So far in quantum chemistry, we have understood how to apply the Schrödinger's equation h psi equal to E psi in order to understand how the wave functions and energies look. The hydrogen atom problem, when solved with the Schrödinger's equation, helped us understand how the concepts of orbitals comes up by itself. We also extended it to the fact where we understood few other aspects like the spin angular quantum number. So let's ask ourselves the question, can we apply it to the helium atom? Okay, so let's go back and try to see how we can set this up. The helium atom has a nucleus. Now, of course, it has 2 electrons. We are going to assume the fact that the mass of the nucleus is much greater than the mass of the electron. So we are going to assume that the nucleus is at the origin, although that need not be the case. There will be small motions that end up coming, but we are approximating it such that the nucleus doesn't move. However, the 2 electrons are in their respective places. So what does this result in? Let's instead of calling them E, we'll call them E1 and E2. E1 for the first electron and E2 for the second electron. And each one of this is referred to its own set of variables of R, theta and phi. So similarly, this electron is going to have okay, so you have 2 electrons whose vectors are shown here. So therefore, how will the Hamiltonian look? The Hamiltonian is going to be minus h cross square by 2 me. It should be 2 mu. But since the reduced mass goes with the lower of masses and we are assuming here the nucleus is so heavy, the mu will tend to mass of an electron. So we'll write it as it is, del 1 square. Okay, and the potential that it ends up experiencing. So what is that potential? Z times E square, because you have a 2E times E that ends up coming here, divided by 4 pi epsilon naught R. Yeah. So this is the equation that we have for electron 1, and the same type of equation can be written for electron 2. H cross square by 2 me delta 2 square, Laplacian again, 2e square. Of course, I missed a 1 here because it has to refer to the vector r1. So this is going to be 4 pi epsilon naught r2. This pertains to electron 2. So what we have written so far is that one half of it is basically the kinetic energy, the other is the potential energy, kinetic energy, potential energy for electron 1 and electron 2. But this doesn't get over here. You realize that these electrons will also end up interacting with one another. As the 2 electrons interact with each other, they have their own potential, which is going to be given by the product of the 2 charges, minus E times minus E divided by 4 pi epsilon naught, and the distance vector between them, R12. Right. So now this is the interaction between the 2 electrons. One is able to appreciate the fact when you view them separately, this is similar to the Hamiltonian for the hydrogen atom problem. This is similar to the same, in fact, if you just change the indices, this is the Hamiltonian for the hydrogen atom problem. And this is nothing but, of course, there is a Z that ends up being different in comparison to the hydrogen atom. And this is the interaction that comes up between the 2 electrons that is going to be not present in the hydrogen atom. If it were a problem where we can separate variables R1 and R2, this could have been easily solved. We are able to see here there is a term that goes as a subtraction between the vectors R1 and R2. So this creates a complication where this can neither be completely put into the first part nor into the second part. It has a contribution that goes with either of them. Okay. If it were indeed the case where they were separable, then what is going to end up happening? Let's say you have H1 plus H2. This is nothing but the sum of Hamiltonians. So the ground state wave function is going to be the product of whatever you get for electron 1 and for electron 2. Of course, this complicates matters a lot. So how can this be experimentally determined is that one can measure the ionization energy of the helium atom, right? The same way we ended up seeing for the hydrogen atom, where you had En given as minus 13.6 by n square eV, where En is the principal quantum number. Here the same thing works out. You are just going to have an additional z square term, assuming it's a hydrogen like atom. When this was measured, they end up getting a value such as minus 78.98 electron volts. So assuming that if it were just the two Hamiltonians H1 and H2 working out, what is going to end up happening? You are going to get something of the sorts 13.6 divided by 1 square times the z number, which is going to be 2 square, plus minus 13.6 by 1 square times 2 square. So this is for each one of them. So this ends up being minus 13.6 by 1 times 4 plus 4, that's going to be 8, minus 109 eV. So one is able to understand the fact this has a poor agreement with the experimental value. And this clearly indicates the fact that the mere summation of the hydrogen atom will not help you explain how this system looks. This is largely because of the fact that we end up having a cross term, which is the interaction term between the electrons, that starts to complicate our matters. So in order to solve this, we should either be able to separate it, which is unfortunately not possible, or we have to resort to other methods that end up coming. And in this case, what we end up doing is to go towards approximation methods. Rather than solving the helium atom in an absolute way, you end up trying to approximate the values that end up coming. The many ways that are available for approximation, and in this class we will only be looking at two major methods. One is the variation theorem and the other is perturbation theory. So let's start with the variation theorem. So what does variation theorem state? It states that, let's say we do not know the actual wave function for a system, assume it as phi. Then if you do end up getting the energy of the system, which is given as phi star, the Hamiltonian for that given system, divided by integral phi star d tau, you actually end up getting an energy which is greater or equal to the ground state energy of the system. Okay, so this is what variation theorem ends up saying. So let me repeat it. Let's say you want to understand a system and you actually do not know its wave function. You can take a trial wave function. In this case, I'm using the symbol phi. And then you can try to use the Hamiltonian for that given system and get the energy as shown here. And whatever energy that you end up getting is the higher estimate. In the best case scenario, if your trial function is well chosen and if it actually represents the ground state, then you will actually be ending up getting the ground state energy itself. Let's take a simple example and try to understand what is that we are trying to pick up from this. So let's go back to the problem that we understood very well earlier on. We were looking at a particle in a one-dimension box. In here, we were able to say the psi was given as square root of 2 by a sine n pi x by a, where x goes between 0 and a. Let's say that we do not know this. We can always take a wave function that, let's say, is c1 times, which is a constant, x times a minus x. Of course, this function has to have all features that we have earlier discussed in the postulates of quantum mechanics, where it should be square integrable, it should be continuous, all the features have to exist for the same. Now let's say we take something of this sort. Let's calculate what is E phi. What are you going to end up happening? You're going to have C1 star times x times a minus x times minus h cross square. Of course, we set the potential to 0 for this problem, by 2m dou square by dou x square x a minus x square. I'm just taking a product of it right away. The whole divided by, of course I missed a c1 here, the whole divided by integral c1 star x into a minus x c1 x into a minus x dx. I'm sure you all would be able to understand the denominator comes because of the fact if phi is not normalized. If it were normalized, this will go end up being 1. And since in this case we are able to realize that it's not normalized, this comes to our rescue. So let's continue deducing this. So E phi is going to be C1 star times C1 integral x into a minus x. We can also write minus h cross square by 2m outside times a differential, second differential of xa minus x square. You realize that the second differential of this term would go to 0 because the first differential will be a constant a, the next differential will go to 0. In this case you are going to get minus 2x and the next differential will be equal to minus 2. So what ends up happening? You get a product with a minus 2 and an integration dx, with a dx there. Of course you got to go between 0 and a. The whole divided by, you have C1 star C1 integral x square a minus x square dx between 0 and a. Good. So let me take this outside. The 2 gets cancelled by itself. The minus term ends up being plus h cross square, and you are also able to see that this term also ends up cancelling by itself, divided by m, and you have an integral xa minus x square dx in the numerator between 0 and a, divided by integral 0 to a x square a square plus x power 4 minus 2a x cube as the integral. So this will be h cross square by m. The integration of this would be x square by 2 within the limits a to 0 minus x cube by 3 within the limits a to 0, divided by, this integral is going to be a square by 3 x cube within the limits a and 0 plus x power 5 by 5 minus a by 2 x4 a to 0. Right? So let's substitute these values, h cross square by m, a cube by 2 minus a cube by 3, that is the numerator, divided by a power 5 by 3 plus a power 5 by 5 minus a power 5 by 2. So simple math is going to help us. All these are prime numbers, so you're going to get something a cube by 6 in the numerator, divided by the whole divided by 30. This is going to be 10 plus 6 minus 15 a power 5. So this will be nothing but, we can cancel some of the terms. A cube can be cancelled to a square, and then you are going to get a 1 here. So the entire term ends up being h cross square by m times 1 over 6 times 30 over 1. So this is nothing but, I still have an a square that comes up from the denominator. So 5 h cross square by m a square. Remember, we always liked writing the solution here with the energy which goes as n square h square by 8 m a square. So therefore for the ground state, this is going to be equal to E1 is equal to h square by 8 m a square, right? And if you take 1 over 8, that's going to be 0.125 h square by m a square. And we have a similar situation here. We have h cross square times 5. So if you sit and calculate it, you'll get a number such as this, h square by m a square. So let us see what we have obtained so far. The actual energy of E0 is 0.125 h square by m a square, while E phi that we have calculated using the variation theorem ends up being 0.12665 h square by m a square. So we are once again able to see the fact that the energy of the ground state that is predicted from the variation theorem is actually higher than that of the E0. So this is what variation theorem says. Let's say you do not know the wave function, you can assume a trial function and get an energy that's a upper bound for the ground state energy. Okay. Now having seen this, can we do something to make this go better? Yeah, it is indeed feasible, but before doing so, let's try to understand some basis for it. Okay, and the basis for this example could be where you can understand the phi can be represented in the eigenfunctions of the particle in a box problem. And remember, the first problem we started with is that we did not know these functions, but we can always assume that they are a complete set. So when you get something like this, let's try to calculate what is E phi. It's going to be integral of Cm star psi m 0 to a, of course, and the Hamiltonian in summation Cn psi n d tau, the whole divided by integral 0 to a Cm star psi m star integral Cn psi n d tau. So this is what we are going to end up getting, and we know we can take the fact that the psi n's are eigenfunctions, right? We know for a fact that these psi n are eigenfunction of the Hamiltonian operator. I agree that we started with the fact that we do not know what is a function, but let's say we still don't know, but we are ending up using the fact that they are eigenfunctions of the Hamiltonian operator. So what is going to end up happening when this ends up operating on the psi n? You are going to get something of this sort: integral 0 to a summation Cm star psi m star energy En summation psi n d tau, the whole divided by, the same case ends up happening here, 0 to a Cm star C I have 0 to a summation Cm star psi m Cn psi n d tau, right? Of course, this is summation over m and n has to be explicitly written. Okay, now having done this, we can simplify this even further. E phi will end up becoming integral 0 to a. We can have the summations outside m and n. Cm star Cn integral 0 to a psi m star psi n d tau, the whole divided by integral m integral n Cm star Cn. Okay, and you know for a fact that these are indeed orthonormal functions, because and we know for a fact that these are orthonormal functions because these were nothing but the eigenfunctions of an Hermitian operator. So what ends up happening? These will vanish to 0 when m not equal to n, and will be equal to 1 when m equal to n. So therefore, the E phi becomes summation m. Actually, it won't be the So what ends up happening? E phi is going to be summation n mod Cn square. I actually missed a En here. En, the whole divided by summation Cn square. Okay, so this is what we end up getting. So now let's try to subtract E0, which is the ground state energy, from this equation, mod Cn square En divided by, okay, minus E0, but I can always write summation mod Cn square divided by summation mod Cn square. This will be equal to 1, and you might remember summation of mod Cn square will also be equal to 1 when normalized, right? So what this ends up doing is that you can actually end up taking this to mod Cn square En minus E0, the whole divided by summation Cn square. So this is very important for us to understand, largely because you know for a fact at best En minus E0 can be equal to 0 when n equal to 0, or En minus E0 is always greater than 0. So this term ends up being greater or equal to 0. Similar is the case for this mod summation of Cn square is always equal to greater always greater or equal to 0. So this indicates E phi minus E 0 is always greater or equal to 0. Therefore, E phi will be greater or equal to E 0. So this is the variation theorem which we ended up applying for a particle in a one-dimension box, and we were able to nicely see this result that ended up coming. So why did we introduce the whole thing? We were able to understand that the helium atom cannot be solved directly and we need approximation methods, and we are first taking the variation theorem route to understand the same. Even before we go to the helium atom, why don't we spend a little more time understanding a few more examples? So let's take the hydrogen atom. Let's say that we do not know the solution of the hydrogen atom problem. We can assume the ground state energy is characterized by e power minus alpha a square. And here alpha is the variational parameter. This parameter will help us to go as close as possible to the ground state energy, meaning that the previous example you are able to understand it's taking you close to the ground state energy, meaning that it's really close to the ground state energy but not exactly same. So can we take it as close as possible? So these type of variational parameters will help you achieve a similar thing. Okay, and here our Hamiltonian is going to be given by minus h cross square by 2 me times 1 over r square dou by dou r square dou by dou r plus the phi terms that end up coming. And for the ground state, we know that L equal to 0, so we don't have to worry about the theta and phi part. Okay, so now let's try to understand what is the E phi that ends up coming for this problem. Of course, there's one more term that I'm missing. That has to be of that of the potential. It is minus E square by 4 pi epsilon naught R. Okay, so that's the entire Hamiltonian that we have at our disposal, and we are trying to understand what is E phi going to be. And E phi can be calculated minus h cross square by 2 me integral 0 to infinity, because r can be between 0 to infinity, r square dr, which has to be put in, times 1 over r square dou by dou r. I think I'm writing this in a little bit of a hurry, so let me not go to the operator yet, because first you need to write the function e power minus alpha r square. Let me not take the by 2, because the textbook does so. We can also take the by 2 and just make the answer a little easier, times the operator. So basically the Hamiltonian operator comes here. Of course this has to be star, since it's a real function it wouldn't make a difference in this case. Okay, so this is what one has to find. So basically we need to put the entire operator into this so as to calculate, and let's try to do that quickly. And of course there's going to be a 4 pi component that ends up coming due to the theta phi components that are present, and the whole divided by, once again there's another 4 pi which comes up due to theta phi component. We're going to have r square dr e power minus alpha r square with a 2, which has to be integrated throughout all space. So in this case I'm going to be invoking a standard integral which goes of this sort: r power 2n e power minus alpha r square dr will be given by 1357 until 2n minus 1 divided by 2 power n plus 1 times alpha power n pi by alpha power half. This is a standard integral. If you do not know, you should be able to get a textbook and find the same. Okay, now having known this, the next step that we have to end up taking is to apply these integrals. Of course, operate the Hamiltonian on this function and expand it and get things going. And remember, there's an r square that ends up coming in other places as well. Okay, so one has to be a little careful. There's an r square that ends up coming. There'll be an r square times this function, which one has to differentiate. So let me rewrite it and carefully do one step at a time. So you're going to have integral 0 to infinity minus h cross square by 2 me e power minus alpha r square times 1 over r square. You have an r square here which can be cancelled now, dou by dou r square dou by dou r of the function e power minus alpha square. Yeah. This is one integral that we have to end up doing, and the other integral that we have to end up doing would be minus, of course I missed a dr here, and then you are also going to have integral 0 to infinity e power minus alpha r square, there is an r square up front, minus e square by 4 pi epsilon naught r, which is the potential, times e power minus alpha r square. Okay, so what did I do? All that we are trying to do is to break this Hamiltonian into two portions. One is the potential energy portion, the other is the, one is the kinetic energy portion, the other is the potential energy portion, and we are applying it serially one after the other. So this is the first component I wrote. This is the second component that will not have this portion, right? So I request you to sit and carefully do these integrals, and the third integral would be of the sort, in the denominator, the whole divided by, we have that integral right there, nothing but this one. So why don't we apply this formula right away? So n equal to 1 in this case, since it's r square n equal to 1, and remember alpha is 2 alpha. So let's say we put in this formula, when n equal to 1 it stops with 1. So this denominator integral is going to be 1 divided by 2 power 1 plus 1, that is 2, alpha, which is 2 alpha because you have a 2 alpha right there, the whole power n, which is going to be 1, product pi by 2 alpha, the whole power half. And then calmly, if you are able to sit and, so that's what the denominator is going to be. Can we reduce this any further? You are going to have 1 divided by 8 alpha times pi by 2 alpha power half. So that's what you have in the denominator. So let's say it's a number, let's say it's a constant c, so the whole divided by c. If you carefully do these integrals, of course there's 4 pi got cancelled. Okay, if you carefully do these integrals, you would end up getting E phi is going to be 3 h cross square by alpha divided by 2 me minus E square alpha power half, the whole divided by square root of 2 times epsilon naught pi power 3 by 2. Okay, so this is what is going to end up happening. The alpha won't go because you have the alpha in the whole term, and if you carefully sit and do this, the integral minimizes to this. Remember, we said the variational parameter alpha would help us go as close as possible to the ground state energy. So the best way to do this is to minimize this function E phi. And how would you minimize it? You would minimize it with respect to alpha. So that is going to end up becoming 3 h cross square divided by 2 me minus 1 half E square divided by square root of 2 alpha. The square root of alpha will come there, epsilon naught pi power 3 by 2. And if you want to find a minima, you want to set the differential to 0. So now what will end up happening, if you do simple arithmetic, you are going to get alpha is mu square, or rather, since I am using me in this case, it will be me square times e power 4, the whole divided by 18 pi cube times epsilon naught h bar power 4, epsilon naught square, because you have to square naught to get alpha, therefore epsilon naught gets squared here. And the important thing one has to understand, you have E phi as a function of alpha and you wanted to minimize it. By minimizing, you mean you take the first differential, set it to 0, and therefore you got the value of alpha where it could be maximum or minimum. Of course, for people who would like to see this, take the second differential with respect to alpha and show that it's less than, is greater than 0 to say it's a minima. Okay, so having done this, you know now you know where the value of E phi will be minimum for a given alpha. You can plug this back in. So instead of doing all that, I'm going to write the answer directly. So E min will happen to be something of the sort of 0.424 times mu square e power 4. Once again I am writing mu square, although I ended up using me square, the whole divided by 16 pi square epsilon naught square times h cross square. Of course, this can be rewritten in terms of A naught, which is what we ended up doing in the class, but instead of spending time on it, let me write what is the actual ground state energy of the hydrogen atom. You end up getting something of this sort. It appears that it's going to be me power 4 divided by 16 pi square epsilon naught square h cross square. Okay, so now once again you are able to appreciate the fact that the E min is greater than that of E naught. We are doing this because even without solving the hydrogen atom problem, by assuming very simple function, we are able to already get very close to the ground state energy of this problem. This is very powerful because let's say you want to attack some other problem for which solving the wave function could be very tedious. Remember, we started the fact that to separate the variables due to this interaction term is going to be extremely difficult. Since that becomes difficult, you are able to understand that we have to somehow get the minimum energy, and by using variation principle, you are able to get very close to the energy. So this is extremely powerful for cases that are unknown and you would like to solve and get the energy of such a system. So let's try to go for a general formalism for these kind of cases to see how this can be done. And for this again, although I claim a general formalism, we will still be solving it for a two-level system. Let's say phi is represented as a sum of Cn psi n. Okay, and we will just take a two-level system problem, psi 1 plus C2 psi 2. Let's take for an example once again the particle in a one-dimension box where the psi 1 is x into a minus x, while psi 2 is x square into a minus x square, the whole square. Remember, these functions are not orthonormal basis set. You don't have to take an orthonormal basis set. You can take any function, and that is what is the power of the variation theorem. Okay, so you can take any function to understand this. And previously, all that we took in the problem of a one-dimension box was that we only took C1 times x into a minus x. Now we are taking more terms. We are not only taking C1 times x into a minus x, we are also taking C2 times x square into a minus x the whole square. Okay, so how would one solve such a problem? What you will end up doing is that we will try to once again find what is E phi. How would you find E phi? You should be doing some integrand of this sort, the whole divided by, since you know that it is not normalized, you have to end up doing the denominator. Of course, in the previous case it was only a function of C1, and in this case it's going to be a function of C1 and C2. And if you saw the example of the hydrogen atom problem where the energy was only a function of the variation parameter alpha, in this case it's a parameter that depends on C1 and C2. So what would one end up doing? Get the dependence of E phi on all these quantities, and then take the differential of E phi with respect to C1 and then E phi with respect to C2, right? Both should be minimum, and therefore solve for that. So basically that's what we are going to end up doing. So why don't we take a look, just for the sake of simplicity, we can try to assume the psi 1 and psi 2, or the functions that we are looking at, are actually real. This need not be the case, they can be complex, that's not a problem. Same way we will also take C1 and C2 to be real, that is not required. If C1 and C2 is not real, you will end up taking the differential with respect to dou C1 star and dou C2 star. So E phi is going to end up becoming integral 0 to a C1 star psi 1 star. We told these are real, but let's write it down for a little bit. Then the Hamiltonian C1 psi 1 plus C2 psi 2 d tau, the whole divided by integral C1 psi 1 plus C2 psi 2 complex conjugate times C1 psi 1 plus C2 psi 2, actually yeah, d tau. right? In this case, it will be 0 to A if you are looking at the particle in a box problem, or whatever the limits that make sense. Okay, now we will get multiple terms that go with it. Remember, these wave functions are not eigenfunctions of the Hamiltonian operator. So you cannot invoke whatever we did earlier, but what will end up happening here is that let's simplify this. You're going to be looking at integral 0 to A C1 star C1 psi 1 star Hamiltonian psi 1 d tau plus integral 0 to A C1 star C2 psi 1 star Hamiltonian psi 2 d tau plus integral 0 to A C2 star C1 psi 2 star Hamiltonian psi 1 d tau plus integral 0 to A C2 star C2 psi 2 star Hamiltonian psi 2 d tau. The whole divided by, probably I should end up writing the denominator in the next page. The denominator is going to be 0 to A C1 star C1 psi 1 star psi 1 d tau plus C1 star C2 psi 1 star psi 2 d tau plus C2 star C1 psi 2 star psi 1 d tau plus integral C2 star C2 psi 2 star psi 2 d tau. Okay, having seen this, one will be able to appreciate the fact we are looking at matrix elements of these operators. So this is nothing but the matrix element, of course, including the integral is going to be h11, and you see that the integral with respect to this will be h12. This is going to be something like h21. This is h22. And these are all complex coefficients that you end up having. Similar is the case where these are integrals between the functions. So we will call them S11. This is going to be S12. This is going to be S21, S22. Remember, the operators that we end up seeing in quantum chemistry are all Hermitian. So therefore, H12 equal to H21. This is because Hij complex conjugate and transpose will be equal to Hji. We have seen this earlier in the postulates. So what will this end up doing? E phi will end up being mod C1 square H11 plus, in this case, since we are looking at C1 and C2 being real, you are going to get H12 plus mod C2 square. You can just say C2 square since we said it's real. The whole divided by C1 square S11 plus 2 C1 C2 S12 plus C2 square S22. Okay, now we have successfully written E phi in terms of C1 and C2. Okay, now having done this, all that we have to do is to take this to the other side. So let's take it C1 square S11 plus 2 C1 C2 S12 plus C2 square S22 times E. I'm not going to write E phi anymore. C1 square H11 plus 2 C1 C2 H12 plus C2 square H22. Okay, now having done this, the first step would be to take the differential with respect to C1, right? So what is that going to end up doing? Remember, if you're taking a differential with respect to C1, this will exist, this will exist, this will not exist. This will exist, this will exist, this will not exist. So let's see what we end up getting. 2C1 S11 plus 2C2 S12 times E plus the entire term dou E by dou C1 times this entire term equal to 2C1 H11 plus 2C2 H12 plus 0. Okay, this will go to 0. The other term goes to 0. And the only reason why we don't have to worry about this is that when you set this to 0, right? When you set this equal to 0, all that we need to compare will be these two terms. So let's try to compare. Let's pool all the C1 terms together. It is going to be, let's say we end up moving this to the right hand side. You're going to have 2C1 H11 minus E S11. Don't forget the E that is present. Plus 2C2 H12 minus E S12 equal to 0. And this is interesting because you can actually immediately cancel these. Okay, and I request you to calmly do the other differentiation, which is dou E by dou C2. But I'll immediately help you understand how the answer will come up. You're going to have C1 with H21 and S21, and then C2 with H22 and S22. So this is going to be, you're going to get something like C1 H21 minus ES21 minus plus C2 H22 minus ES22 equal to 0. So this is what you're going to end up getting. So with these two equations, let's call this equation 1 and this is equation 2. You can actually construct a matrix where you're going to end up having H11 minus ES11, H12 minus ES12, H21 minus ES21, H22 minus ES22 times C1 C2 is equal to 0. Of course, you cannot set C1 and C2 to 0 because then that gives you a trivial function. Therefore, this entire matrix has to be equal to 0, and this is actually what is called the secular determinant. And what we see here is that the secular determinant, which is H11 minus ES11, H12 minus ES12, we did say that since these are Hermitian, these are going to be complex conjugates of each other, and since you're taking real, these two are going to be one and the same in this example, meaning that we took psi and c to be real, so therefore they are going to be same. So you want to solve this. So this is nothing but the H minus ES determinant that you want to solve to 0, and one is able to immediately appreciate the fact that this is going to be a quadratic equation with respect to E. Therefore, you are going to get two roots, and you will take the smaller of the two roots, which will be the higher estimate for the ground state energy. Okay, so I hope you are able to understand when you are taking a problem where you can actually, you don't have to take the simplest of functions, you can take a more complicated function where we take a summation over a set of functions that you end up having, and let's say that these functions end up being orthonormal to each other, then some of these terms will end up becoming 0, which we'll see in a moment. But they don't have to be orthonormal to each other. We can use them as they are and solve for E. That will give us what is the upper bound for the ground state energy. Okay, now having understood these many aspects, the only thing that stops us from understanding anything more is going towards the helium atom. The helium atom problem, we were able to understand that when you just club two of the hydrogen atoms, you get an energy estimate which is extremely poor in comparison to the experiment. If you have to go more closer, it's clearly understood that the interaction energy has to be factored in. Okay, let's see how this gets solved. So one can always take the function as the product of the 1s orbital that we ended up having. So what is the product of the, let's also write the function for the 1s orbital. It is going to be something of the sort 2 root 2 divided by root of pi, right, times 1 over a naught power 3 by 2 followed by e power r minus r by a naught. So this is the function we saw for the hydrogen atom. So now we have two such. So we can take a product. So you're going to get 2 root 2 square. So that's going to be 8 divided by pi times a naught power 3. And you're going to have a function e power minus r1 plus r2 by a naught. Let's say this is the trial function that we end up taking. Okay, this is a psi 0 that you end up taking. And then you apply h psi equal to e psi. When you solve for this, when you just apply this with the Hamiltonian that we have deduced, you are going to get something of the sort 8E1 plus VEE times psi 0. Remember, the 8E1 comes from whatever we had seen earlier. It comes from this aspect. You have a 2 square plus 2 square that gives you 8 times E1, where the E1 is the energy of ground state of hydrogen atom. Okay, so that's how you get this. We already saw it's minus 109 eV that we are trying to see. Now we understand that if the electron interaction potential can be solved for, one will be able to get the necessary value for the energy minimum. I would request you to take a look at how this gets solved. Rather than spending more time on solving for the math, I request you to take a look at the Griffiths textbook, chapter number 7, the variation principle, where they end up solving in section 7.2, and you would be observing that VEE comes to about 34 eV. So therefore, what ends up happening, the energy minimum will now, therefore, the predicted energy minimum will be minus 109 plus 34, that ends up being minus 75 eV. So one is able to understand by just taking the 1s orbital of hydrogen atom and estimating energy already comes up very close. The experimental value was minus 78.98 eV. So from minus 109, you are able to get it closer to the experimental value. Of course, we can definitely do better, and all that one has to do is to make the parameter z that we ended up using as the variation parameter. So let's say instead of choosing the function as we had taken earlier, you take z cube times pi a naught power 3 times e power minus z r1 plus r2 divided by a naught. Now you have z as the variation parameter. Let's say you get energy for this and then try to minimize with respect to z and follow the entire ordeal. You would be finding that the energy can be estimated to be equal to minus 77.5 eV, getting even more closer to the experimental value. One can further refine these kind of functions and to get as close as to the reality, but many times once you get within a certain error, you actually don't worry too much about improving it any further. So I hope this lecture helped you understand how even when you do not know the function of a given problem, you can assume any function and actually get the value of energy. This lecture goes beyond the scope of trying to understand and predict how this psi can be chosen, but overall I hope the learning objective here is satisfied, where you are able to realize there is a secular determinant that we end up getting for a two-level system where we took C1 psi 1 plus C2 psi 2, we have a 2 by 2 matrix. And when you expand it to an n-level system, you're going to have an n by n matrix which goes of this sort: H11 minus ES11, H12 minus ES12, so on until H1n minus ES1n, H21 minus ES21, H21 minus ES21 until H2n minus ES2n, and then so on, such that it goes to En1 minus Hn1 minus ESn1, Hn2 minus ESn2 until Hnn minus ESnn. If this gets solved, you're going to get n roots, and the lowest of the roots would help you get what is an estimate of the higher estimate of the ground state energy. Okay, so this is how, of course, as you keep adding more and more functions, you might be able to get more closer to the experimentally determined value. Okay, and let's say your choice of wave functions to begin with are already orthonormal, then what ends up happening, these terms would end up going to 0. So you're going to finally, in such cases, you're going to have matrices that look like this. Only the diagonal elements are going to be a little more laborious, but all the other off diagonal elements become pretty simple. Now it will be H2n, Hn2, Hn3 until Hnn minus ESnn. Okay, so this becomes a little more easier to solve, and therefore people can actually take a function that. So therefore people can represent their state with the functions that they desire, taking a complete orthonormal basis set and find the energy of the ground state. Okay, so one can further take this to other examples. You can solve the particle in a one-dimension box where now you have put it under a potential. Until 0 to a by 2, the potential increases as with a slope v1, and then after that it decreases with a slope v1. Okay, so here once again we can actually take psi 1 and psi 2 the way we have used, which is 2 by a sine n pi x by a. We can actually use the same functions that we have learned from the class, and you can try to form a combination of this c1 psi 1 plus c2 psi 2 and try to solve for it. Okay, and when you are solving for it, remember there is a potential, meaning that it is the Hamiltonian is just not going to be equal to dou square by dou x square, but you are also going to have a potential term. This potential is going to be v1 times x for values 0 until a by 2, and then v1 times a minus x for a by 2 greater than x less than or equal to a. Okay, this has to be punched in, and let's say you sit and solve for this problem, and in this case we know for a fact that the psi 1 and psi 2 are orthogonal to each other. The matrix is going to look something of this sort. So this is a matrix where once again you are going to get 2 powers of e, and the answer that I would write here directly, these are the 2 solutions that end up coming. In this case it's a little tricky to find out which one is of a minimum value, which we'll discuss in a moment. The other root is going to be h square by 2 ma square. In this case both are positive roots, none of them are negative roots. If you got a negative root you could have eliminated it. Okay, now here the lower of these values is going to be determined by these parameters of m, a, v1 that would decide whether let's say EA and EB, whether EA is smaller or EB is smaller. But overall one is able to understand, let's say I give you a problem to solve where taking the particle in a one-dimension box problem between 0 and A, and I give you a step function for the potential, meaning that the potential is 0 until this part and the potential is equal to V0 after half of the box. We should be able to solve that. Of course, the potential at these sides are infinity. We should be able to use psi 1 and psi 2 and solve the same problem to understand what is the value of the ground state energy. Okay, so I hope this lecture has helped you understand how variational theorem could be used towards understanding systems that have either a resemblance with whatever we have learned before, or is completely new where we can end up assuming functions and have the ability to get the ground state energy. I request you guys to sit and work out this problem, which is given as a solved example in the Macquarie textbook, which would help you once again get the experience to solve these problems with minimum errors.